So you have a proof, but once you've gone through the proof, you're no more the wiser why it's true. It gets the job done, but it doesn't give you any intuition. So what I want to give you today is a probabilistic proof, which I think gives you much more intuition about what is going on. Just like the original Green-Niehaus-Wilf proof of this gives real intuition about what the hook lengths are doing there. And in fact, so much intuition that Doron himself took the algorithm that they had in their paper and made it non-probabilistic because he wanted to see what it would look like if he made it deterministic. Okay, now the second thing that I should say is that the proof I'm about to show you today is not my own, strictly speaking. What happened is the following. So I had been giving talks about the probabilistic proof I'd come up with for this at various venues, including the joint math meetings in San Francisco this January. And at the end of my talk, I always like to give open problems. And I gave an open problem talk, and two people came up to me afterwards and said, I think I know how to solve this problem of yours. And in so doing, they gave what I will consider perhaps an even better probabilistic proof of this, for reasons that I'll tell you later in the talk. So I'm going to show you their proof, which of course was inspired by my proof, and there's a substantial overlap, but there's a crucial point.
You give a proof and ask for an extension?
No, I'll need to say more things at the end of the talk before you understand why they came up with this second proof. But their proof technique is more powerful. It can prove things other than this. That's the short answer. So this proof is due independently, by the way. These two people were not working together. They just both happened to be in the audience, and they both found the same proof at once. David Rabiner and a student of Don Rawlings, Tiefenbrook. And since it is kind of based on what I did, I'll say it's a la Sagan. Although, as I said, there's a crucial point where they had a brilliant insight, which I see. Okay, well, how are we going to start out? Well, let's multiply both sides by n factorial. Why do I want to do that? Well, if I do that, on this side I'm going to have n factorial over the product of the hook lengths. And we know what n factorial over the product of the hook lengths is, right? It's the number of increasing labelings. Okay? And use the hook formula. So therefore, you will get an equivalent formula that we wanted, which says that the sum over all binary trees of the number of increasing labelings of that tree times the product of 1 over 2 to the h of e minus 1 should be 1, which is even nicer than 1 over n factorial. Okay, so here is how I propose to prove this. First of all, by killing myself. I do want to show you this, then I'll kill myself. So I claim, in order to prove that, it suffices to find a probabilistic algorithm generating labelings, increasing labelings, L of binary trees with the following two properties. First property, the probability that this algorithm produces a given labeling is exactly that product that we're interested in. notice at this point. This means that this probability doesn't really depend on the labeling. It only depends upon the underlying tree. Any two labelings with the same underlying tree will have the same probability. That'll be crucial in just a little bit. And then the second is the obvious thing that we want this to be a probability distribution in the sense that if I sum over all possible labelings, their probabilities, I should get 1. Right? Why do these two things give you that equation? Well, just think about it for a second. If we know that this sum is equal to 1, we can plug in what we're given as the probability of each labeling, right? So plug this into this formula. What will that give us? Well, it'll give us this. Right? But remember what I just said. This is the same for each increasing labeling of a given tree. So we can take all of those products, which are the same, and add them all up. If we do that, how many times will we get each one? Well, clearly the number of increasing labelings, which we know is ft. So that is equal to the sum of all trees. Right? So I'm just combining elements in my sum to get that. Okay, so does everybody agree with me that if I can give you an algorithm that does 1 and 2, I will be done? I see nods of approval, or at least nobody's willing to admit that they do. Okay, so how do we do that? Well, again, it's not very hard. In fact, it's almost ridiculously easy. So everything I've shown you right now was in my original proof, but here's the crucial place where the algorithms are different, very crucial type of thing. They're both simple, but theirs has a nice, so that's the algorithm. So first of all, you start, as you probably would imagine, with a root labeled. What a root must be labeled? 1. Okay. Now you're going to grow the tree in the following manner. So you're going to partition uniformly at random the descendants of 1. So that is the set from 2 up to n into 2 subsets. I'll call the one subset S, and you should think of S as the left descendants of 1. And also a set T, which of course is going to be the rest of them. So that will be the right descendants of 1. Okay, so now I've told you 1 is here, it's S, these guys are going to be on the left, these guys are going to be on the right. And then I essentially iterate, right? Since it's an increasing labeling, what must the left child of 1 be? Well, it must be the smallest thing in this set, right? Because things have got to get bigger. So make min S the left child of 1 and iterate, right? That is to say, break S up into 2 pieces, which are the left and right, and similarly with T. So, quick example.